I'd like to welcome everyone back after the holiday break and wish everyone a good 2021. A reminder that the meeting is being recorded, and we ask that you stay on mute during the talk, except feel free to unmute yourself and ask questions at any time. I'm delighted to introduce Masoumeh Zarei from the University of Augsburg, who will speak on torus actions on four-dimensional Alexandrov spaces.
Thank you very much. I'm very pleased to be here, give a talk, and I would like to wish you all a happy and healthy new year. I'm going to give a talk on torus actions on four-dimensional Alexandrov spaces. It's a joint work with Diego Corro and Jesús Núñez-Zimbrón from they're now in Mexico. Let's start the talk by the goals that we have. The first goal of the talk is to present a set of invariants for an effective and isometric T2 action on a closed orientable Alexandrov space, which classifies X up to equivariant homeomorphism. This means that if we have a T2 action on another Alexandrov space, then they are equivariantly homeomorphic if and only if they have an isomorphic set of invariants. This is the first goal. And the second goal is that assume we are given a set of invariants. Can we construct an Alexandrov space in dimension 4 with an effective and isometric T2 action, such that the set of invariants that we get from the first part is isomorphic to the set that we are given. So, we show that, yes, we can construct such an Alexandrov space. So these are the goals of the talk. And let me focus first on the works that in the previous studies that we have. So there is a work by Orlik and Raymond in 70s where they obtained an equivariant classification for T2 actions on closed orientable four-dimensional smooth manifolds. And they further showed that if we have a continuous effective action on a topological manifold, then it is equivariantly homeomorphic to a smooth action of T2 on a smooth four manifold, meaning that the equivariant classification in topological category is the same as the equivariant classification in the smooth category. And this is a very important point that we will use in this work. And then Orlik and Raymond and Corro independently obtained a homeomorphism classification of T2 actions on four manifolds, and they showed what these spaces are. And in the end, the non-orientable case was addressed by Kim in 1993. Note that here I'm just mentioning the works of on T2 actions on four-dimensional manifolds. Of course, there are other works in other dimensions. For instance, there is a S1 action on three-dimensional manifolds and also on three-dimensional Alexandrov spaces by Jesús. And in dimension 5, or even in the presence of curvature conditions. So there are many other works, but I only mention these results because they are directly related to my work. Okay, let's recall you first the definition of Alexandrov space. The idea behind the definition of Alexandrov space is to compare the triangles in a metric space with the triangles in a model space. And the model space is model space M2K is a two-dimensional simply connected Riemannian manifold with constant curvature K, which are S2 if K is positive, H2 if k is negative, and Euclidean plane if k is 0. Okay, a length space, which is a metric space, such that the distance between any 2 points is the infimum of length of curves connecting these 2 points, is said to be a space with curvature bounded below by some constant k if every point has a neighborhood such that for each triangle in this neighborhood we have this condition. So the condition says that if we have a triangle in our Alexandrov space, and then we consider the comparison triangle in the model space, which is a triangle such that the sides of this triangle is the same as the sides of our triangle. So this side is equal to this one to this one, and so on. And then if I choose a point on one of the sides like D, and the corresponding points on the comparison triangle D bar, I mean by corresponding point, I mean this side is equal to this side, then the distance between A and D is bigger than or equal to the distance bigger than or equal to the distance between A bar and D bar. Roughly speaking, our triangles are fatter than the triangles in the model space. If such a thing happens, we say that the length space has curvature bounded below by k. And a complete locally compact length space with curvature bounded below by k is called an Alexandrov space. An immediate example is a complete Riemannian manifold with a curvature bound on the sectional curvature by Toponogov's theorem. Then there exists an important class of examples, namely the Gromov-Hausdorff limits of a sequence of Riemannian manifolds with a uniform lower bound on their sectional curvatures. Or there are ways that we can construct Alexandrov spaces, like if I am given Riemannian manifolds with sectional curvature bounded below by 1, and then I construct the suspension of this space. That is, I construct the cylinder and then I collapse 2 sides. This is also an Alexandrov space with curvature bounded below by 1. So as you see, Alexandrov spaces appear naturally in Riemannian geometry. There is an important notion related to Alexandrov spaces, which is the space of directions. It is defined as follows. At each point, you consider the set of all geodesic directions. You endow it with the angular metric, and then you take the completion of this metric space. This is called the space of directions, and it is denoted by sigma xx. It is known that space of directions is a compact Alexandrov space with curvature bounded below by 1, and its dimension is equal to dimension of x minus 1. Space of directions are very important notion for Alexandrov in the theory of Alexandrov spaces, because they give us the local picture of Alexandrov spaces by Perelman's conical neighborhood theorem, which says that every point has a neighborhood which is pointed homeomorphic to the cone over space of directions. Now, in the presence of a Lie group action, we have a nice description of the orbit space. It says that if we have an isometric action on an Alexandrov space, and we, in each orbit, which is a Riemannian manifold, we take the tangent space, and this tangent space, we take the sphere. And we take the perpendicular space to this sphere, that is Sx perp. It is all element of the space of directions, which is perpendicular to all elements of the unit spheres in the tangent space of the orbits. Then Fernando and Catherine Searle showed that the space of directions is isometric to the join of this sphere and the normal space of directions. This is a very useful tool in our work here. As it is customary in the transformation group theory, a very useful tool is the slice theorem, which is proven for the Alexandrov spaces by John Harvey and Catherine. And it is as follows. It says that around each orbit, the neighborhood around each orbit has this expression. And as you see, we can see that the normal space of directions in this expression. This is also a very useful tool because it gives us the local picture of the space under the action of an isometric action of a Lie group. Okay, with this short review on Alexandrov spaces, let's see how we can get the set of invariants. This is the setting. Let X be a closed, orientable four-dimensional Alexandrov space which admits an effective and isometric T2 action. The orbit space is denoted by X star, and small x star is the image of an orbit under the projection map. Yeah, these are what we want to assume. And then, as I said, the understanding that we get from the orbit space, from the space of directions is very important. Remember, we are in dimension 4, and the space of directions is a three-dimensional Alexandrov space with positive curvature. Such Alexandrov spaces were classified by Fernando and Luis, and it says that every positively curved Alexandrov space in dimension 3 is either the suspension of RP2 or a spherical space 4. Okay, but in our case, since we assume the orientability of Alexandrov spaces, this cannot occur. And among the spherical space forms, only spheres and lens spaces with non-trivial fundamental group can occur. Why? Because T2 also acts effectively on the space of directions. And if we look at the classification, and so it is a cohomogeneity 1 action. And if we look at the classification of cohomogeneity 1 actions on three-dimensional manifolds, we see that only the lens spaces and S3 admit such actions. Therefore, in our situation, the only possibility for the space of directions are either S3 or a lens space with non-trivial fundamental group. I divide these two because they're important to be distinguished, as you will see next. Okay. So now you can see why it is important to divide, to distinguish between S3 and lens spaces with non-trivial fundamental group. We say that a point is topologically regular if its space of direction is S3. Therefore, there exists, it has a neighborhood which is homeomorphic to R4. So it's a topological point. It's a manifold point. And otherwise, it is topologically singular, meaning that the space of direction of topologically singular points are lens spaces with non-trivial fundamental group. From now on, when I say lens space, I really mean with a non-trivial fundamental group. Okay, I should recall you again the results of Orlik and Raymond. Assume we have closed orientable four-dimensional Alexandrov space, which is topologically regular, meaning that the underlying space is a topological manifold. As I said, Orlik and Raymond showed that the T2 action on such spaces is equivariantly homeomorphic to a smooth T2 action on a smooth manifold. So the equivariant classification is the same as the equivariant classification in the smooth category. And therefore, in this situation, we don't get something new. That's why in this, throughout the talk, I assume that the set of topologically singular points is not empty, meaning that I always have a point whose space of directions is a lens space. Okay, the first thing to do is to find the possible isotropic groups. Okay, one of them is T2 itself. One of them is the circle subgroup. This is isomorphic to S1, and it is denoted by GMN. It is defined in this way. And then we have the finite cyclic group. And then we have the trivial group. Yeah. So there are other subgroups of T2, but they do not appear as isotropic groups here because of the effectiveness of the action and also orientability and other properties that we have. Now the goal is that to associate a weight to each point in the orbit space, which is related to the isotropy information of the action, and then to see, to find a local picture of the orbit space. And by those information, we get the weights. And this local picture is given by the slice theorem. Let me quickly give an example and then go through the general cases. Consider the cohomogeneity one action of T2 on a lens space. It is given by a group diagram like this, T2, two circle subgroups. And then this is something that I should point out. So NPQ, the determinant of this matrix is plus minus R. And so this thing is the determinant of this matrix. And this is very important, as you will see. And then we define an induced action of T2 on suspension of the lens space. It is defined in this way. So T2 acts on suspension of the lens space. Layer wise. So if we have the suspension, it acts on each level. Okay, and then I want to describe the action, the orbit space, and the isotropic groups. Okay, the isotropic groups that we may have are Gx to be T2 for fixed points. Gx could be GMN or GPQ coming from the cohomogeneity one action that we have, and Gx is 1 for the principal orbits. And then we use these results by Fernando and Catherine, which says a space of direction is isometric to the spheres, unit spheres in the orbit space joined with Sx perp. Because we know what the dimension of the orbits are, it is easy to find the circle, the spheres, and then by that we can find Sx perp, because we know the classification of Alexandrov spaces in low dimensions, And also we can find the space of directions. And then if we use a slice theorem, we see that a neighborhood around a point x star in x star is the cone over Sx perp mod Gx. And again, we have a classification of Gx that we know what they are on Alexandrov spaces that we know. For example, if G of x is T2, then the space of direction is equal to the normal space of directions, and this is the length space. And therefore the cone over, so maybe I write it here, the cone over the Sx perp mod T2 is cone over length space T2. It is cone over, it's a homogeneity 1 action with weights GMN 1 and GPQ. So what I get is something like this. It's a cone. Here we have the fixed point, x star, and then I associate to the points on this arc, GMN, and the points on this arc, GPQ. These are the weights that associate to these points in the orbit space. And you can easily see from the action, if this is, assume this is the suspension of the length space. So since the action is layer-wise, and on each layer we have a homogeneity 1 action, then the orbit space is a disk. There are 2 fixed points going to going to 2 points on the boundary, and then if these 2 fixed points are connected by an arc, that I give the weights GMN to them, and another arc that I give weight GPQ. And I want to summarize this information in a set. So this is the orbit space is a disk. Therefore, it's a 2-dimensional manifold with genus 0. It has an orientation because I gave an orientation to the Alexandrov space that I have. I show it in this way, and then I have this information. To show this information, I use this notation GMN. Then the determinant of these 2 circle subgroups, MQ minus NP, and then GPQ. I claim that this action is characterized by this information, but we will see it later. Okay, this is more or less what we do to get the weights. So I quickly show you how the possible isotropic groups are, the local structure of the orbit space are, and how the points are distributed on the orbit space, and then give you the weights. Okay, for those points whose isotropic groups are T2, meaning for the fixed points, we can see that the space of directions are either a 3 or a length space. If we analyze the via the slice theorem, the neighborhood of x star in the orbit space, we see that it is like a half disk. The fixed point is on the boundary, and then if you see, it is actually an isolated fixed point. We don't have any other fixed point in this neighborhood. And then there are 2 arcs, which are corresponding to the points with the isotropic groups GMN and GPQ. And as I said, it's a boundary point. It is topologically singular if and only if this determinant that I pointed out is not 0 and it is not plus minus 1. This is a very important point. And it is topologically regular if and only if this determinant is 1. So for fixed points, we get this information. And then we have the circle subgroups. For those points whose isotropic groups are circle subgroups, the space of directions is S3. Again, we have such local picture for the orbit space. And as you see here, X star is on the boundary, and this whole arc has GMN as its isotropic group. As I said, it's a boundary point. It's topologically regular because space of direction is S3. And then the exceptional orbits. For those orbits, or for those points, the space of directions are S3. And the local picture in the orbit space is a cone. And this point is the apex of this cone. Again, you see that we have X star, and then around X star, everything is a principal orbit. Therefore, exceptional orbits are also isolated. Their interior points, and they're topologically regular, as you can see. And in the end, we have those points which exist on the principal orbits. The space of directions are S3. The local picture, again, it's a cone. Therefore, their interior points, and they're topologically regular. Now I collect all of this information and I get this result, that assume X is a closed orientable four-dimensional Alexandrov space with an effective isometric T2 action. Then we have these things. The first statement says that the orbit space is a two-manifold. As you said, all the local pictures are either a disk or a half disk. So it's a two-manifold, possibly with boundary. The interior points consist of the principal orbits and exceptional orbits, finite number because they're isolated and it is compact. And then the boundary components. We have boundary components which entirely consist of circular orbits. And we have boundary components that we have fixed points, either topologically regular fixed point or topologically singular fixed point. Okay, now by this information, we can collect the weights. First of all, the first weight is the genus of the surface that we got. So the first weight is the genus. And then if I fix an orientation for T2, and we have an orientation for X, then via the projection map, we get an orientation for X star. So the second weight is the orientation. And then the next weight is related to those boundary components which entirely consist of the circular orbits. So we show them by this notation. And then we have the boundary components which have fixed points, and we use this notation. Let me explain this notation a little bit. So this is the Lth boundary component, and A, L, B, L, F, L is AL1, BL1, this one. And then I have FL1 and AL2, BL2. So this FL1 is the determinant of AL1, BL1, AL2, BL2. And this is the point that we understand if this point, this fixed point, is topologically regular or topologically singular. If FL1 is plus minus 1, it is topologically regular. If it is not 1, plus minus 1, and note that shouldn't be 0, then it is topologically singular because it is a lens space. It gives us a lens space. And then we continue. So this is also one of the weights that we have. And in the end, we have this weight. This weight is related to the exceptional orbits. So this alpha j is the isotropic group, and this gamma j1 and gamma j2 is related to the action of alpha j on d2 times t2. Why? Because the slice that we have around these points are d2 times t2 mod z alpha j. And the action is given by z alpha j acts on t2. If lambda is the generator, is lambda to the power of gamma j1 z1, lambda to the power of gamma j2 z2. And the action of z alpha j2 on d2 when we consider it as a unit disk in C is just the usual action. Note that we normalize the action such that here the power is 1, and we can always do that. The important point is that these weights completely determine the action, and the action of z alpha j on d2 times t2. Okay, so these are the weights, and now I can give you the set. If we have a four-dimensional Alexandrov spaces close-oriented with an effective isometric T2 action, then we associate to each orbit space this set of weights. If you look at the weights that I have here, epsilon is orientation, genus, circular orbits, regular fixed point or singular fixed point, and exceptional orbits. I have a new weight here. It didn't appear in our computation because it appears when C union RF union SF is empty, meaning that we don't have circular orbits, fixed points. But because I assume that I always have a topologically singular point, this is not empty for topologically singular Alexandrov spaces. That's why it didn't appear. But in general, we have this weight. It is a second cohomology class, which is related to the extension of sections, as you can somehow see in the next sections. Okay, these are the weights. But now the question is that, are they really invariants? Meaning that if I have a torus action on another Alexandrov space and I get the same weight, then are the two Alexandrov spaces equivariantly homeomorphic? In this part, I show that they are indeed invariants. So let me define what do we mean when we say two orbit spaces are isomorphic. This is what we expected, meaning that there exists a weight and orientation preserving homeomorphism between the two orbit spaces. Okay, now with that, we have this theorem which says, assume we have two closed oriented Alexandrov space with effective isometric actions. X and Y are equivariantly homeomorphic if and only if X star and Y star with those weights are isomorphic. It's clear if X and Y are equivariantly homeomorphic, X star and Y star are isomorphic. The problem is the converse. X star and Y star are isomorphic. We want to show that X and Y are equivariantly homeomorphic. The main idea of the proof is to show that there exists a cross-section to the orbit map. And to show that, there are several steps. The first step is as follows. Remember, the exceptional orbits were interior points with and also isolated. I consider a very small disks around each exceptional orbit. They don't intersect, and they only have one exceptional orbit. Then I can use abstraction theory to show that I can define a section on the boundary of each disk. So the first step is to construct sections on the boundary of each disk. Now I want to extend it, but little by little. To do that, the first thing that I do, I remove the annular neighborhood around the boundary components. And I'm left with such space X1 star. I took out the disks around exceptional orbits. I took out the annular neighborhoods around boundary components. And I'm left with this one. If I use abstraction theory, I see that the sections that I constructed on the boundary of these small disks can be extended. Okay, now I want to extend this section on the annular neighborhoods of the boundary component. So I take X2 star to be X star minus this small disk in the interior around the exceptional orbits. So note that first of all, I start with the circular orbits. A tubular neighborhood around a circular, around a boundary component with circular orbits is something like this. And then this proposition helps me. It says if I have a compact Hausdorff space with an effective T2 action in a very general case, and the orbit space is a cylinder, such that the upper circle corresponds to the points with GPQ as the isotropic groups, and the rest corresponds to the principal orbits. Then, given any section on this blue part on the lower circle can be extended. If we go back, we are in this situation. I have a section on this blue part, and I want to extend it to this whole to this annular neighborhood. This proposition helps. Then I go to the annular neighborhoods of the boundary components with fixed points. There they look like this. This one, or this is from the, when we look from the top, from the above. It is something like this. And now this proposition would help me. This proposition says that, okay, I have a compact Hausdorff space with an effective continuous T2 action. And the orbit space is a rectangle. And on one side, I have a fixed point. On this side, the left points of this fixed point corresponds to those orbits with isotropic groups GMN. The right points correspond to isotropic group GPQ, and the rest are principal orbits. If I have such an orbit space for my action, then given any section, given a section on any part of the boundary, I can extend it. So if I have a section on any part of this boundary, I can extend it. And now I go back to my annular neighborhood. I divide it in this way. And I'm exactly in the previous case, meaning that I have a rectangle like this. I have a fixed point. Here I have circular orbits. Here I have circular orbits. From the previous steps, I have a section here. By the proposition, I extend it. Now I go to the other one. I have section here, section not here. Here I extend it. And now I have a section here, I have a section here, I have a section here, I extend it. In this way, I construct a section from x2 star to x. Okay, we have constructed this section, and now we take the inverse image of x2 star. Remember, x2 star were the subset of x star, where we took out the small neighborhoods around exceptional orbits. And now we take the inverse image under the projection map. So for x and for y, those spaces that we had. From the cross-section theorem that we have, we construct an equivariant homeomorphism. Now, what is missing from the original Alexandrov spaces that we have are the neighborhoods around exceptional orbits. But as I said before, the neighborhoods around exceptional orbits are completely determined by the weights that we have from the action of cyclic groups on T2 and on D2. Therefore, we can glue them back to X2 and Y2 in a unique way, and in the end, we get the equivariant homeomorphism that we wanted. Okay, now there is a question. I showed that if I start with a torus action on an Alexandrov space, I get a set of invariants, and I showed that it is really a set of invariants. Now the question is as follows. Assume I am given a set of invariants. Can I construct an Alexandrov space with an isometric T2 action such that the set of invariants that I get is isomorphic to the given set of invariants? And the answer is yes. Assume we have a legally weighted topological 2 manifold with weights this. When I say legally weighted, I mean here these determinants shouldn't be 0. Why? Because if they're 0, then by the classification of cohomogeneity 1 actions on 3 manifolds, we know that the manifold should be S2 times S1. And S2 times S1 cannot occur as the space of directions of an Alexandrov space. Therefore, when I say legally, I'm requiring that this FL is not 0. Okay, I'm given a legal set of weights. Then there exists an orbifold with T2 action such that the orbit space of this orbifold is isomorphic to X. Why this is true? It goes back to the work of Hefliger and Salem when they constructed an orbifold for this type of information. So what is this information? It says if I have a paracompact space, a very general situation, and I have a covering for it, Vij's is a covering for Vi's is a covering for this W. And then I have an orbifold with T2 action, Tn, this is for general n. And so we can construct for each piece an orbifold. And we have this local, compatibility condition on the intersection. For each point in the intersection, we have a neighborhood like W, such that if I take pi I inverse of V here, or I take pi j inverse of V here, I can construct a Tn diffeomorphism, a Tn equivariant diffeomorphism between these two subsets. We call them compatibility condition. And then what they showed is that to every compatible local data is associated a cohomology class in H3 of W and Z, whose vanishing is equivalent to the existence of an orbifold with a Tn action, such that, okay, if this is the orbifold that we construct, X, and then we have W here, but remember over Vi we had another orbifold, Tn orbifold. It says that pi inverse of Vi and Xi are locally Tn equivariantly diffeomorphic. So how this theorem helps us in this way? First of all, we are in a good situation. Why? Because the orbit space that we have, okay, I may use abuse of language to say orbit space, but I mean the two-dimensional manifold that I'm given. So of course, we don't have action yet, but okay. So I have a two-dimensional manifold, and if I can construct such a local, compatible local data for my manifold, then I have this condition for free, because it is the third cohomology class of a two-dimensional manifold, and it is 0. Therefore, my main challenge is to find these compatible local data for the topological, for this two-dimensional manifold with these prescribed weights that I have. Okay, now let's see how we can go through it. The first step is to find the covering. To find the covering, I do this. I divide the boundary components in two groups. The first group consists of those boundary components which consist entirely of circular orbits, or those fixed points which are topologically regular. Assume that we have Q, the number of them is Q. And then the second set is those boundary components that we have singular fixed points. Okay, this is the first step. Then around those boundary components that I have singular fixed points, I consider two neighborhoods. One of them is ui star, which is the smaller one, and then wi star. Note that this wi star shouldn't intersect. Okay, I have these neighborhoods around boundary components with singular orbits. And then what I do is that I take out the UIs, the purple one. So I take out this part. What I am left with is one of the elements of the orbitals, of the covering. And then I need to cover the annular neighborhoods of those boundary components which has singular fixed points. And therefore, for around each fixed point, I consider such a neighborhood. And I assume that each neighborhood has only one fixed point. So this is one of them, and this is one of them. So these are our covering. Then I need to construct orbifolds. The second step is to construct orbifolds for each open subset. Okay, for y star, what I do is that I consider this set of invariants. If you look at this set of invariants, everything is similar to the one that I was given initially, but there is a difference here. I only have those boundary components with fixed points, which are related to topologically regular. This plus minus one is telling me. And then I go back to the result of Orlik and Raymond. I see that there I can construct a smooth orientable manifold with T2 action. So for this one, I construct some y tilde with T2 action. And I consider the orbit space. So to get the orbit space, to get y star from y tilde star, what I do is that I take T plus S minus Q, the number of boundary components with singular fixed points. I take this number of points, interior points, I take very small neighborhoods around them, and we take them out. What I'm left with is, in fact, y star. Okay, then I take pi inverse of y star. This is the first orbifold. This is actually a manifold. This part is a manifold. Okay, this is one part. And then, around the fixed points, singular fixed points, we have such a neighborhood. And this Fij, this determinant, again helps us to define the desired orbifold with the desired action. So if this Fij is 1, the orbifold that I construct is in fact an open disk. If it is not 1, the orbifold that I construct is a cone over the lens space. And the actions are nothing but the induced action from cohomogeneity 1 actions. Okay, I constructed the orbifolds, now the compatibility condition. Okay, so we have y star and one of the neighborhood around fixed points. It is homeomorphic to a rectangle, and if I take it A, then I have pi y and pi y inverse of A, and then I have pi ik inverse of A. One could show that this is equivariantly diffeomorphic to this space. This is also, therefore, I can define an equivariantly diffeomorphism between these two pieces. And then those neighborhoods around fixed points here. So if we call it B, then we have pi ij, here it's pi ij inverse of B. Here I have pi ij plus 1 inverse of B. Again, one could show that they're equivariantly diffeomorphic to cone over S1 times S1 times an interval, and this is the same. And therefore, we can define an equivariantly diffeomorphic map between these two pieces as well. Okay, so we are almost done. By Salem and Hefliger, we constructed a smooth manifold, orbifold with T2 action. They admit Riemannian orbifold metric, and then using the same technique or similar technique as in the Riemannian case, via this averaging argument, we can construct a T2 invariant Riemannian orbifold metric on our orbifold, which is in particular an Alexandrov space with an isometric T2 action. So in the end, we have this corollary that if X is a closed orientable four-dimensional Alexandrov space with a T2 action, then X is equivariantly homeomorphic to an orbifold with a smooth T2 action. And by that, I finish my talk.
Thank you very much for a very nice talk. Are there questions?
About the last step on the last slide.
Yeah.
No, the slide before, sorry, about the metric.
Yeah.
So do you start with a metric on the quotient space for this construction? I didn't quite get that.
No, so we construct a smooth orbifold, and like Riemannian, like smooth manifolds, orbifolds are also admit Riemannian orbifolds. So we have a smooth orbifold, we construct a metric on this orbifold, and then what we need is that this metric should be T2 invariant. And then somehow the same technique as in the Riemannian case, we obtain a T2 invariant metric on our orbifold. So it's just construction of a Riemannian orbifold metric on a smooth orbifold.
Ah, okay, so you make the metric T2 invariant by construction.
Yeah.
Ah, I see. Thank you.
Other questions? If there's no other questions, let's thank the speaker again. And our next talk is 2 weeks from today it'll be 7 p.m. UTC time, 3 hours later than today's talk. And the speaker will be Sam Lin. So thank you very much.
Thank you very much.